Have you ever looked up at the night sky and felt a sense of awe? The sheer scale of the cosmos is almost impossible to comprehend. But what if I told you that an equally profound and mysterious universe exists in the opposite direction? We will travel past the scale of molecules and atoms, beyond the protons and neutrons that form their core. When we think of something small, we might picture a grain of sand. Science, however, has taken us much deeper. We discovered the world of cells. For a long time, the atom itself was considered the final frontier. Physicists, driven by an insatiable curiosity, smashed these particles together in colossal accelerators. They discovered that even protons and neutrons were not fundamental, a scale so mind-bogglingly small that a single atom is as large in comparison as our entire solar system. This is the Planck scale, the ultimate flaw of physical reality. The Planck scale holds the key to the most profound mystery in all of modern physics. It is the meeting point of our two greatest theories about the universe: general relativity and quantum mechanics. The problem is, these two pillars of physics are utterly incompatible. There are two places in the known universe where this happens: at the singularity inside a black hole, and at the very beginning of the universe in the Big Bang. To understand the origin of these fundamental units, we must first meet the man whose name they bear, Max Planck. Born in Germany in 1858, Planck was a brilliant but cautious physicist. The problem that consumed Planck at the turn of the 20th century was known as the black-body radiation problem. The existing theories suggested that such an object should emit an infinite amount of energy at high frequencies. He proposed that energy, which everyone assumed was a continuous flowing quantity like water, could only be emitted or absorbed in discrete tiny packets or quanta. This single idea, that energy comes in packets, was the seed from which all of quantum mechanics would grow. In simple terms, they are a set of physical units of measurement based only on universal physical constants. The meter was originally defined as 1/10,000,000th of the distance from the North Pole to the equator. Planck realized that by taking a few of the universe's most fundamental numbers, the speed of light, the gravitational constant, and his own new constant related to quantum energy packets, these would be units that any intelligent civilization, anywhere in the universe, could independently discover and calculate. The Planck length, for example, is about 1.6 times 10 to the minus 35th meters. To put that into perspective, if you were to scale up a single atom to the size of the entire observable universe, the Planck length would be about the height of a single tree. To truly appreciate the elegance of Planck units, we need to look at the ingredients that go into making them. The first ingredient is the speed of light in a vacuum, known as c. The second ingredient is the gravitational constant, known as g. It is what holds you to the Earth, keeps the Earth in orbit around the Sun. The final key ingredient is the one Planck himself introduced, the reduced Planck constant, written as h-bar. It is the fundamental constant that tells us the universe is granular and probabilistic at its core. Let us begin our deep dive with the most famous of these units, the Planck length. It is the fundamental pixel of space, the shortest possible wavelength. To pinpoint something at the Planck length would require an incredible amount of energy packed into a tiny space. At the Planck length, the energy required to make the measurement would be so immense it would create a microscopic black hole. This concept is at the heart of theories like loop quantum gravity, which proposes that spacetime is woven from tiny, indivisible loops of this fundamental size. It is a profound clue about the ultimate nature of space itself, hinting that what we perceive as empty void is in fact a seething network of quantum information. If the Planck length is the smallest pixel of space, then the Planck time is its temporal equivalent. Instead, it might proceed in a series of tiny discrete steps, like the individual frames of a film. In the single second it takes you to say the word one, more than 1 trillion Planck times have elapsed. At the moment of the Big Bang, the entire observable universe was compressed into a space smaller than a proton. Any successful theory of everything must be able to explain what happens during these unimaginably short intervals. It is the ultimate now, the indivisible moment of cosmic reality. After grappling with the infinitesimal scales of Planck length and time, the Planck mass comes as something of a surprise. A hypothetical particle with the Planck mass would be a true quantum black hole. Our final destination in this tour of fundamental units is perhaps the most extreme of all, the Planck temperature. If you were to try and heat a system beyond the Planck temperature, something extraordinary would happen. At this point, the entire concept of individual particles begins to dissolve into a primordial soup of pure, chaotic energy. The temperature would be stuck at this ultimate limit, a cosmic thermostat set by the laws of quantum gravity. To truly grasp why Planck units are so profoundly important, we must first appreciate the greatest challenge in modern physics, a deep and troubling chasm. On one side of this divide stands general relativity, Albert Einstein's magnificent theory of gravity. On the other side of the chasm lies quantum mechanics, the theory of the subatomic realm. Unlike the clockwork certainty of relativity, the quantum world is a place of inherent fuzziness. The two theories, when forced together in these extreme conditions, simply refuse to cooperate. The Planck scale is not just a collection of tiny numbers. It is the arena where the battle for supremacy between our two pillar theories is waged. The breakdown of our existing theories at the Planck scale is not a cause for despair, but rather a tremendous opportunity. Two main contenders have emerged in this monumental quest, both of which take the Planck scale as their fundamental starting point. The first is string theory. The second leading approach is called loop quantum gravity. You can think of it as space-time being built from fundamental, indivisible atoms of space and time. Both of these ambitious theories are still works in progress, facing immense mathematical and conceptual challenges. However, their very existence is a testament to the power of the concepts laid out by Planck. The connection between Planck units and our fundamental theories goes even deeper. When you write the laws of physics in this natural language, their deep interconnectedness becomes brilliantly clear. They are the fundamental conversion factors of the cosmos. By setting them to one, we are adopting the universe's own perspective, a viewpoint from which these concepts are unified. They are the point where space becomes time, pointing the way to a deeper and more elegant simplicity. Let us venture in our minds into the world of the Planck scale. What would we find there? He imagined that if we could zoom in on space-time to the level of the Planck length, the smooth, gentle curvature described by Einstein's relativity would dissolve into a chaotic, turbulent, and ever-changing seascape. For a brief moment, a particle and its antiparticle might spring into existence from nothing. Miniature wormholes, bridges connecting different points in space-time, could be forming and vanishing in an instant. On our large scale, all this frantic activity averages out to the smooth, stable space-time we know and love. Understanding this foam is one of the greatest challenges for any theory of quantum gravity, as it represents the fundamental texture of our universe. Let's explore another thought experiment, one that truly highlights the bizarre nature of the Planck scale. So, to see the Planck length, we would need a particle, perhaps a photon of light, with an immense amount of energy. Now, this might not sound like much, but remember, we are trying to cram all of this energy into a single subatomic particle. So, in our attempt to observe the Planck length, we would create a particle with so much energy that it would instantly collapse into a microscopic black hole. The very thing we wanted to measure would be hidden forever behind an event horizon. The universe has a built-in privacy setting. It forbids us from ever directly observing distances smaller than the Planck length. Our journey to the Planck scale leads us to one of the most mind-bending ideas in modern physics, the holographic principle. A physicist named Jacob Bekenstein was puzzled by the entropy of a black hole, which is a measure of its information content. Instead, it is proportional to the surface area of its event horizon, the two-dimensional boundary that marks the point of no return. The fundamental unit of information in this holographic description is encoded on a tiny area of the boundary surface, an area equal to 1 square Planck length. We may not be characters in a cosmic play, but rather holographic projections from a cosmic hard drive. It is a powerful example of how thinking about the limits imposed by the Planck scale can lead to a complete revolution in our conception of what reality is. All of these thought experiments, the quantum foam, the black hole microscope, the holographic principle, point towards the same startling conclusion. The Planck length is the size of these cosmic pixels, and the Planck time is the time it takes to refresh the screen. If reality is made of discrete units of information, then the evolution of the universe from one moment to the next could be seen as the running of a vast cosmic algorithm. The complexity and richness we see around us emerge from the processing of these fundamental bits of information at the Planck scale. So, where does this journey into the infinitesimal leave us? It leaves us standing at the edge of the greatest unsolved mystery in all of science. The search for this theory, whether it be string theory, loop quantum gravity, or something else entirely that we haven't even imagined yet, is the primary driving force of theoretical physics today. A complete theory of quantum gravity would allow us to understand the origin of the universe itself. So physicists must become detectives, searching for subtle, indirect clues. This quest is a testament to the relentless curiosity of the human spirit. The quest to understand the Planck scale is a multi-generational endeavor. Our exploration of the Planck scale brings us full circle, back to that sense of awe we feel when looking at the night sky. The universe is just as vast and mysterious in its smallness as it is in its largeness. The existence of the Planck scale forces us to question our most basic assumptions about reality. These aren't just technical questions for physicists, they're deeply philosophical inquiries into the nature of existence. So, the next time you look up at the stars, I invite you to also think down. Think about the incredible hidden world that exists beneath the surface of everything you see. The universe has written its most fundamental rules on the smallest of possible canvases. By trying to read that impossibly small text, we're not just learning about physics, we're learning about the ultimate nature of reality itself. And that is a journey that's always worth taking, a story of wonder that will continue to inspire us for centuries to come.